Hello everyone, and let us see the greedy approach, one of the greedy approach. So we have already seen greedy approach to form a minimum spanning tree using Kruskal's and Prim's minimum spanning tree techniques. So let us see the Dijkstra's shortest path technique, which is one of the greedy approach. Now it is called as greedy approaches because the person named Greedy had invented it. So let us see how to find shortest path from one vertex to all other vertices in the graph, of course with minimum number of edges. So here we will have a weighted graph. Now again for Dijkstra's algorithm, we can have a weighted graph, of course, and it can be a directed or indirected graph. So either the graph will be directed graph or an undirected graph, but weight will be associated with every edge that you have, and that edge weight which is associated with that edge will be considered as cost for this particular algorithm. So it would be cost to travel from one vertex to another vertex. Now to solve this Dijkstra's shortest path technique, let us see how it is done. Now the question that can be asked is, you will have to find the shortest path from vertex 1 to all other vertices which are present in the graph. So of course, as I told you, the graph can be directed or undirected, but then weight will be associated with every edge that you have in the graph, and this edge will be considered as cost. Now to start with, what you will have to do first is you will have to construct an adjacency matrix for the given graph. So as we all are aware how to construct an adjacency matrix, the number of rows are equal to the number of edges in the graph. So here I have 5 edges, so 5 rows, and 5 edges, 5 vertices, so 5 rows. Similarly 5 vertices, so 5 columns. And then if there is no edge between two vertices, then we mark it as infinity, or I couldn't write here infinite, and that is why I have written infi. Similarly, for the vertex, like for example 1 to 1, I don't have an edge, so I mark it as 0. And then all the other vertices which are adjacent to one particular vertex, we have written the weights. Okay, so this is a weighted adjacency matrix for the given graph. Now here, so your first duty is to construct an adjacency matrix, which is already done here for you. So from 1 to 1, I have no edge, so I mark it as 0. Then from 1 to 2, I have an edge with weight 10, so I wrote here 10. Then 1 to 3, I don't have an edge, direct edge, because 3 is not adjacent to 1, and that is why I've written infi. So when there is no edge at all, then you write it as infinity. And then from 1 to 4, I have an edge with weight 30, so I've written 30. And then 1 to 5, I have an edge again whose weight is 40. Now my duty is to have all the vertices in the graph in the minimum spanning tree that I form, but with minimum number of edges. So I'll find the shortest way to travel from 1 to 2, or from 1 to 3, or from 1 to 4, or from 1 to 5. So for doing that, what I will do is I will create two arrays. One is distance matrix and the other is visited matrix. So I have two arrays, one is distance and the other is visited. Now distance matrix will be for one vertex from which I want to find shortest path to all other vertices. Like for example here, I have to find out shortest path from vertex 1 to all other vertices in the graph. So I'll create a distance matrix for vertex 1. Similarly, now if I want to find out shortest path from 3 to all other vertices, then I'll construct a distance matrix for vertex 3. Similarly, if I want to I want to find out shortest path from 4 to all other vertices, then I will have distance matrix for vertex 4. Okay, so this is how you form a distance matrix for that particular vertex which is asked. Similarly, I'll create a visited array also, where once I visit that particular vertex, I'll mark it 1. Right now, I have not visited any of the vertex, and that is why I mark it 0. So all the vertices are unvisited right now, and that is why I mark it as 0. So visited, which means that you have already visited that vertex, and unvisited, which means you have not visited that vertex. So that will help you to traverse the graph easily. Okay, so what is how do you start with? You first construct an adjacency weighted matrix for the given graph. Then, as you know that when you are forming this adjacency matrix, so if there is a direct edge, then you mark weight of that edge. If there is no edge at all, then you mark it as infinity, and for the same vertex you mark it as 0. So this is the first thing that you will do. Second is you will have a distance and vertex arrays to declare. So distance matrix will be for vertex from which you want to find shortest path to all the vertices. So here I have already, if you can see the last two lines, distance matrix for 1 is already framed. So from 1 to 1 distance is 0. Then from 1 to 2, what would be the distance that I need to travel? 10. From 1 3 I don't have an edge, so make it infinity. 1 to 4, what is the distance to travel from 1 to 4? 30. And 1 to 5 40. So that is nothing but my distance matrix for vertex 1. And then I have created a visited array where all vertices are unvisited, and that is why they are marked as 0. So this is what is the first thing that you will do when you are finding the shortest path from vertex 1 to all other vertices. Let us go ahead. If you have understood this in a proper way, then we will go ahead. And now our steps begin to find the shortest path from vertex 1 to all other vertices. To start with, what you will do, so your step number 1 is you will find the adjacent vertex to 1. What do you mean by adjacent vertex? All the vertices which are immediately connected to 1. So here 2, 4 and 5 are adjacent vertices to 1. So first what you do is you select that vertex. So you first mark 1 as visited, and then you select the vertex which is adjacent to 1. So here we have 2, 4 and 5. I select 2. I have selected 2. You can select 4, you can select 5, any vertex you want. But usually we go from left to right, and that is why I have selected 2. Now you select this 2, and in visited array you mark it as visited, because now you are trying to find out the shortest path from 1 to all other vertices to which are adjacent to 2. So what you are doing in short is you are trying to find out the shortest path from 1 to 3, 1 to 4 and 1 to 5 via 2. This is what you are doing. So you have selected 2, and now you try to identify all the adjacent vertices to 2. So adjacent vertices to 2 are 3 and 1. But 1 is already visited, so you leave 1. Now what you are going to do is you are trying to find out the shortest path from 1 to 3 via 2. So how to do that? So distance from 1 to 2, which is 10. So this is how you write it. So distance 2 plus cost of 2 3. So distance from 1 to 2 is 10, and cost from 2 to 3 is 50. You add 50 plus 10, which is equal to 60. Now in distance matrix from 1 to 3, if you see, you had marked it as infinity. Look here. So this was infinity. Of course infinity is less than, or rather it is greater than 60. So I need to make that change here. I have to write here less than, right? So of course it is less than 60, and that is why you can update your distance matrix, and that is why you update your distance matrix, because infinity is always greater than 60. So I can go from 1 to 3. So shortest path from 1 to 3 via 2 can be done. and that is why you updated your distance matrix, where instead of infinity you wrote 60. So this is your step number 1. What you did in step number 1, you took vertex 1. Now it is asked from 1 to all other vertices, so starting point is 1, and then you find out adjacent vertices to 1, which are 2, 4 and 5. You selected any one of them, so I selected 2. Then 2, I find out adjacent vertices to 2 which are not visited. 1 is already visited, so I leave it, and then the next non-visited is 3. So what I do is I try to find out the distance from 1 to 2 plus cost from 2 to 3. So I'm trying to find out shortest path from 1 to 3 via 2. The shortest path from 1 to all other vertices via 2. But then only 3 is adjacent to 2. 4 ला जाता है इतने, 5 ला जाता है इतने. That is why I leave 4 and 5, and I find out the shortest path from 1 to 3, which is 60. And this 60 is of course less than infinity, so I update my distance matrix. Then in step 2, now your next adjacent vertex to 1 is 4. So now you try to find out shortest path from 1 to all other vertices via 4. So now you come to 4, mark it visited. So my 4 is marked as visited, and now I try to find out adjacent vertices to 4. So here adjacent vertices to 4 are 3 and 5. 2 is not adjacent to vertex 4, and that is why I leave it. 1 is adjacent to 4, but then 1 is already visited. So what do is I try to find out all the adjacent vertices to 4 which are not visited. So 5 is not visited and 3 is also not visited. So I try to find out shortest path from 1 to 3 via 4 and 1 to 5 via 4. Now there is a direct edge from 1 to 5. Maybe this value can come greater than 1 to 5 via 4. That can also happen, and that is why you try all possible things so that you find out shortest path from vertex 1 to all other vertices. And that is why to do that I find out first the distance matrix of 4. So distance from 1 to 4 plus cost of 4 to 3. I calculate addition of this, so that comes to 50. That is from 1 to 3 via 4, my cost came is 50. Now in distance matrix I had this value as 60. If you see here, your distance matrix, distance from 1 to 3 is 60, and the newly calculated value via 4 is 50. So distance from 1 to 3 via 2 was 60, and 1 to 3 via 4 is 50. Who is less? 50 is less than 60, of course. So you have to update your distance matrix. So what I'll do is, instead of 1 to 2 and then 2 to 3, what I'll do, I'll go from 1 to 4 and then I'll go from 4 to 3. So this is how I'll travel from 1 to 3. Next adjacent vertex which is not visited is 5 to 4. So I then distance from 1 to 4, which is this formula, distance of 4 plus cost of 4 to 5. So cost of 4 to 5 is 60. So I add 30 plus 60, which is equal to 90. Now in distance matrix I already have 40. So distance from 1 to 5 is already 40, which I can see by naked eye also. And then distance from 1 to 5 via 4 is more costlier, 60 plus 30, which is 90. 90 is of course more than 40, and that is why I do not update my distance matrix for this. I only update one value, which is 50. So my new distance matrix now is 0, 10, 50, 30 and then finally 40. Now your 2 is visited, 4 is visited. Now left out is 5, which is adjacent to 1. Now what we can do is, we can find out distance from 1 to all other vertices in the graph via 5. So I can go from 1 to 2 via 5, I can go from 1 to 3 via 5, I can go from 1 to 4 via 5 and then 1 to 5. So I am trying to find out shortest path from 1 to all other vertices in the graph via 5. Of course, if the remaining vertices are adjacent to 5. Like here, for example, I'm trying to find out the shortest path from 1 to 2 via 5. But 5 is not directly connected to 2. So I'll leave 2. I'll not bother about 2. Then I'm trying to find out shortest path from 1 to 3 via 5. That is possible because 3 is directly connected to 5. And then I'm trying to find out adjacent vertex from 1 to 4 via 5. That is also possible because I direct edge is connected. Okay, so what am I trying to do in every step? I'm trying to find out the shortest path from one vertex to all other vertices via a single vertex. Like I'm trying to find out shortest path from 1 to all other vertices via 2, from 1 to all other vertices via 4, 1 to all other vertices via 5. Why not 3? Because 3 is not directly connected to 1. Why did I select 1? Because in question only they have asked me that you have to find out shortest path from 1 to all other vertices, and that is why I have selected 1 as the vertex. So now let us go ahead and try to find out the shortest path from 1 to 3 via 5. So how to do that? Distance from 1 to 5. The formula, remember the formula, distance plus cost. So distance from 1 to 5, because 5 is adjacent to 1. So distance from 1 to 5 plus cost of 5 to 3. So what is distance from 1 to 5? 40. And what is cost of 5 to 3? This is 10. So here I forgot to write the value, but it is 10. So 40 plus 10 is equal to 50. Now what is the distance from 1 to 3? Here in updated distance matrix it is 50. What value you have calculated? The value that you have calculated is 50, which is of course greater than 40, isn't it? And that is why we do not update the distance matrix. Okay, then at step number 4, so all the vertices are over. Of course, one adjacent vertex to 5 is 3 and 4. And why did we go to 3? Why did we select uh, 3? Is because 4 is already visited. So I go to 5, which is next adjacent vertex. I mark it visited and find out adjacent vertices which are adjacent to 5 but not visited. 4 was already visited, and that is why we took distance from 1 to 5 and cost from 5 to 3. That's it. So finally, if you see now, mm, this here again I have not taken the distance from 3 to 5, which is 10. Okay, so please take a note of this. So now the remaining vertices which are not visited is only 3. Rest all vertices are visited. So what we have to do is we have to mark it visited. Then distance from 3 plus cost of 3 to 3. So distance from 3 is 50 in distance matrix, and then cost of 3 to 3, which is 0. So once I get it is 50, again I do not update the distance matrix. So the final spanning tree for using the Dijkstras shortest path technique is nothing but the one you can see. So from 1 to all other vertices. So from 1 to 2 I have 10. Then 1 to 3 I can go via 4. So 1 to 4 and then 4 to 3 and then 1 to 5 directly. So all the vertices are included in your spanning tree, but with minimum number of edges. So this is how you create a shortest path from one vertex to all other vertices in your graph. So this is your final step where you draw the final graph with minimum number of edges and the shortest path from the asked vertex to all other vertices. I hope you have understood the Dijkstra's shortest path technique clearly. Thank you for patiently listening. Thank you again.